Okay. So in this other 45 minutes, we should try to stay on time because then there is a linear colloquium at 3:15. So we are going to speak about a real-world example where they took an optimization problem and they ran it on the wave. So it's a paper by so the problem is called the flight gate assignment. I don't know why this is happening. I never in my life use the phone with the sound on. And never people call me, by the way. Sono a insegnamento, Simone, scusami, ti chiamo dopo. Okay, sorry for this, with big embarrassment. Okay, and it's, I put the reference. So it's still unpublished, but and you will see it's not entirely satisfactory because they try to solve this problem on a quantum annealer, and you will see that they have to pre-process so much their instances that eventually they cannot really run significant instances due to this problem that you were mentioning, that I will talk again about, of the limited connectivity of the wave machine, and the need for an all-to-all connectivity in this problem. So basically the problem is the one of maximizing the comfort of passengers in an airport by minimizing the time that they spend at the airport itself. And this can be divided in different contributions. So there are passengers that are transferring from when the flight comes to the exit, and this is a certain number of passengers. Let's say are those that are arrived with the flight I, and they spend a time that is the arrival that depends on the gate alpha. So we are going to have a set of flights that are labeled by I, and they run in the set F. And then we are going to have a set of gates that are labeled by alpha, and they belong to the set G. So then the T arrival alpha is the time that the passengers that arrive at gate alpha employ to go from the gate to the exit of the airport. Then there are those who come through the check-in and they want to go at the gate. So then this is the departing time. So then there are an I departure, and they want to go at flight alpha also of departure. So they have a certain time, and then there is a transfer time where passengers arrive at a certain gate and they have to go at a different gate. So it's a sort of transfer time that is, so the number of these passengers is Nij, it depends on the two flights, I and flight J, and the time depends on the two gates, alpha and beta. And it's called the time, alpha beta. Okay, quite intuitive. So then we are going to use the same formalism as before and to assign binary variables that tells if a certain flight I has to be assigned to a certain gate alpha. So these are our binary variables xi alpha that are going to be 1 if flight I is assigned to gate alpha and the 0 otherwise. So with this, one can already write down the cost function, which is the total time. At least a part of it. I'm going to come back on this. So we have the time of arrival and departure that depend on x. So either one or the other, they are going to be formally written the same, so I write them only one with the superscript. So this is the sum over all the flight and all the gates of the number of passengers either arriving or departing, and the time that it takes to the gate, times if effectively flight I is assigned to gate alpha. And then this is correspond to these two parts. We still have to take into account the transfer time. So then the transfer time is the sum over I alpha j beta of n ij t alpha beta x I alpha x j beta.
So T alpha for the arrival and departure, that's the arrival time of that flight?
No,
or?
It's the time that it takes when a flight arrives at gate alpha to the passenger to go from the gate to the exit, or when it's the arrival. When it's the departure, alpha is the time that it takes for the passenger that exited check-in, so they arrive at the airport, to go to what's called it?
To go to that gate.
To that gate.
Okay,
exactly.
I see. Thank you.
Yeah. Okay. Then, so you can already see that we want to optimize the sum of these cost functions. So we are going to write that the total cost function that we want to optimize is t arrival x plus t departure x plus t transfer x. But actually there is not the end of the story. So this is the so-called unconstrained part of the problem, but there is also some constraint that would correspond then typically constraints map very easily to decision problem, and then you have to write down the minimization version of it, like a little bit like we did before for some of the problems. So what are the constraints? The constraints are that every flight obviously can only be assigned to one gate. You cannot assign one flight to two gates. So the way to write it is that the sum over alpha of x I alpha must be equal to 1 for all I that belong to f. And then another constraint is that a gate can be occupied by a single flight. So at a gate there must be maximum a flight or 0 flights. So then the sum of the two binary variable x alpha I x alpha j must be equal to maximum 1 for each gate alpha. So then this we write it like xi alpha plus xj alpha is smaller or equal to 1. And then since these are binary variables that can only be 0 or 1, it is possible then to rewrite it in the quadratic form xi alpha times xj alpha is equal to 0. It's just because when xi can only be 0 or 1, the two conditions are equivalent. Okay, and then out of this, actually, we want to obtain functions to be minimized So then we are going to write the difference of this like some term to be minimized, and the difference of this like some term to be minimized. So then the constraint.
Excuse me.
Yes.
So this is all at one instance, right? I mean, at some instance t, because you say that there can only be one flight to assign to one gate, right? But then that's not I mean, after that flight is gone away, that gate is free again.
Yes.
So that is not catered to here.
Yeah, no, it's taken into account. That's fine. But they have another bunch of variables that they introduce.
That's not taken into account.
There is a time buffer. Yes, it is taken into account. Actually, it's a little
okay.
bit more complicated, like of what I'm doing it. But at the end of the story is that you can model it like this.
Okay.
There are more details in the paper. So they introduce also a time of buffer, which is the time between two flights at the same gate.
Okay.
Then they write the constraint of the in terms of this buffering time, and then eventually they simplify it like this. And I don't think that they lose anything in the simplification. I will think about it later. Let's rediscuss it later. At the same gate. Yeah, let's rediscuss it later. Okay, so then the way how in practice this is translated is with these two extra terms that are going to be added to the cost function, which are this, then it's penalty terms, which is just taking that we penalize when this is not verified. So when this is not verified, this is larger than 0, and then it's a penalty term in the Hamiltonian. And this is the same for the C of not having two flights at the same gate. Yeah, now I remember. Yes, because these are going to belong, now I remember the answer to your question. These are going to be I and j that belong to a certain set P that is defined with the time of the buffer.
Okay.
So
Okay.
this is how they do. These are not all the ij.
Okay.
So, and P depends on the buffer. Okay. Okay, then the total full cost function is t of x. Plus, then we put a certain coefficients in front of the penalty terms. And in practice, so you see that this should be chosen as big as possible in principle, because you want potentially even going to infinity, because you want this constraint to be really satisfied. But then in practice, this is problematic to run on the wave, because there are problems with when this becomes too large. It's difficult to embed the coefficients and embed the problem in the wave machine, basically. So then they are limited by that, and they have a lot of technicalities to choose what is the best compromise for these numbers. What I wanted to make you notice is, so now this is written as you see it in terms of a quadratic cost function. So now if we want, we could do the mapping that we did before, where we map the binary variables into spins, and we write this into a Ising Hamiltonian. We could do that. But with the wave, it's not necessary, because the wave supports this form for optimization problems that is called, by the way, QUBO. QUBO stands for quadratic unconstrained binary optimization. Unconstrained quadratic, it's obviously quadratic in the binary variables. Unconstrained means that we cannot support directly this expression unless we put them in this form, where we want to minimize something. And yeah, this is binary optimization. By the way, yeah, I think you three know already what is the wave, but maybe for the record is what has been advertised as the first word functioning quantum computer. That is quite impressive engineering, from the engineering point of view, architecture with superconducting qubits. There are 2,000 in the one that has been used for this paper. So they are based on superconducting Johnson junctions, and they are then cooled down, and the problem is that there is not really a very, very, very high control on the quality of these qubits, and we don't know if they are all coherent. Probably they are not all coherent for the full annealing time, and there have been people who have been trying to assess whether this is really a quantum computer or not, and so what we know is that it behaves as a quantum device, so you cannot really simulate what it does classically. Matthias Streuer is a person who for years has been carrying the studies. What we don't know is if really it can provide a quantum advantage. This we don't know. And we don't know if it is working as like a perfect quantum computer should be, probably not. So if it's still open, like if the wave doesn't provide speed up, it's still open, maybe a perfect quantum annealer will, because the wave is not a perfect quantum annealer. So, and for the moment they were only able to show constant advantage in terms of time to solution with respect to simulated annealing, which is one classical algorithm. So it's not the best one. The constant advantage was impressive, was 10 to the 5. There was a paper by John Martinez and the Google group assessing the performances of the wave on a specific problem. But it's still, it has been, of course, a topic of debate. And yeah, so it's still a very much open question. But for this problem, so what they do, now, by the way, the general Kubo form is what we wrote here. You can also write it down. Okay. So this is the general Kubo form, and as I was saying, with the wave, when you program, you can just give this, and it will transform it in a annealing Hamiltonian, like in an Ising Hamiltonian, and do the annealing for you. Then, in practice, what they do, so they take data from a real world, from a German airport, and the data, as you can imagine, they provide the flights. So they provide I, F, G, and then they provide the number of passengers. They don't provide the times of transfer, of course, because it's not easy to track. So they perform some simulation to derive what the times should be. And then they have a lot of instances, say 163 instances, and these are too big to be fit on the wave. Then also one thing that they notice that the part that is responsible for make it difficult for a classical optimization to solve this is for the coupling terms, these ones. Because if we only had a single, like linear terms, then it would be very easy to do this optimization with the currently known algorithms. So then what they do, a lot of pre-processing to fit the instances that they have. So first they plot the graph of the connectivities, then they isolate some cluster problem that is clusterized. They also do something like, they discard all the flights that were arriving on the day before, and or where the departure and the arrival was into different days. And they are left with a certain number of instances, So
But technically you only need 1 qubit per, is it 1 qubit per flight or 1 qubit per gate?
1 qubit per binary variable.
Yes.
So per if you assign a flight to a gate.
Okay, I see.
Yeah, is this xi alpha. So 163.
Oh, so it's 1 qubit per possible combination.
So flight into gate.
No, if you assign one configuration would be the full solution, like if you assigned all, like which gates are assigned to each flight. And this is one single variable is if flight I is assigned to gate alpha.
Yeah, but then you need to sum over I and alpha, right?
Mhm.
Like, you,
Yeah.
so that's so it's 1 qubit per combination of flight and gate.
So number of flights and a number of gates, right? You need that many number of qubits. Is that pretty clear?
Yeah, we need flights times number of
Yeah.
flights, number of flights times number of gates.
Yeah.
So F times G.
Yeah,
Yeah.
that's
Yeah,
that more
yeah,
qubits you need.
Yeah,
So,
yeah.
okay, so you actually it actually scales very fast with the number of.
Mhm. Yeah. No, but actually no, because it's combinatorial. It's not even the product. That like.
Oh yeah.
Wait. So
No,
yeah,
it
it's the
is.
problem is combinatorial. So if the length of these two would be the same, it would be with the factorial, you know, or
No. Okay.
it's like assigning 100 flights, so like what I said before, assigning 100 guests to 100 chairs. You can do it with 100 factorial.
Yeah,
So I
so
suppose
that's number of different combinations.
Yeah. So I suppose that assigning, yeah, that's the number of different combinations. Yes, how you can assign F, like 100 flights to 100 gates. Then this becomes absolutely intractable, as we said before. Like,
But
and
yeah,
then a number of qubits.
I think it's what you wrote. Like you'll get a 2 by 2. Sorry, you'll get a F times G matrix, right? And if there's 1, it means that they are assigned, and if it's all the zeros, it will be a very sparse matrix.
Mm. Yeah, I don't think that they write it very explicitly the number of qubits, but I think you're right. It must be
Yeah.
that. Yeah. But to give you an idea of how difficult it is with real life problems, so even here in the beginning, like at some point of the preprocessing, they are left with 163 instances with flight label from 1 to 16, and gates that are labeled from 2 to 16. And this could fit on the wave 2000, but there is a problem that the coefficients that if you do this, then the coefficients that I obtain here in the t, so these coefficients here, or the cubo basically, these cubo coefficients, they are still to spread to match precision requirements for the wave. So it doesn't go. And they have to do further preprocessing that is called beam packing, where basically they have to map both the number of passengers and the number of, and the times. Yes. And the times. They are both mapped to integer sets of numbers that go from 1 to nt. And this goes, and passengers, and this goes from 1 to n times. And now, so, and then in this they have a certain integer numbers then. So this of course changes not the structure, but changes the coefficients of the problem. And therefore, they still have to check first that it doesn't change it too much, so they define an approximation ratio. that tells you what is the ratio between the solution that you would obtain with so what the value of the cost function that you would obtain with the real values for the number of passengers and the times, and the ones that you do with bin packing with these integers, and then they verify that it's not too bad basically. And now with all of this machinery, they are left with, so this corresponds then to 84 binary variables. And now there is this problem, is that the connectivity of the wave is a specific one, it's not all-to-all. Maybe from this, maybe they don't also have all-to-all, but they have like definitely a very messed up connectivity. And the wave, what they have is a specific thing, it's called a chimera graph. And it looks like this. I put the picture is from the, it's from the website. So they have unit cells of 8 qubits. These are physical qubits, and they are connected in this way. So they are connected like this, and they are connected like this. Yeah. So this is connected like this, and this is connected like this. So basically, the idea is that these are connected to all of these. These and these are connected to all of this, but they are not all connected because they don't have connectivity of this and of that. And then these are blocks of such modules. So then it's not like the qubits are clearly not all connected. Then you have these blocks here, yeah. So then each of these is going to become a logical qubit. And the way, so the reason why one gains with this embedding is that within this, even if they are not all connected, for instance, this is not connected to this is not connected to this, and I think also these are limitedly connected from one to the other. So say that this is connected to this, and this to this. But then if you do this embedding, you gain a lot in connectivity. Because basically any of these connectivities that goes out of one block, if you define this as a physical qubit, logical qubit, you can, then you are connected to 4 other cells instead of only one, basically. And then they have this structure repeating. So basically, with this is one of the possible embeddings. There are other. One other famous is called after Zoller, Leuchner, and another person. I don't know. I think I put it. It's in the notes, but there is another famous embedding. But anyway, for the wave, you need this one. Then the thing is, how then are you going to do if they all disagree? How can you recover like that you're when you map the Hamiltonian into this? So it doesn't work. Basically, what they have to do is that you have to enforce very strong ferromagnetic coupling in one block, so that all the qubits here agree on the value, basically. So then, in terms of physical qubits, they must add to a Hamiltonian a terms that say, in each block, I want all the qubits to agree. Because then this becomes really a logical qubit and with a majority vote, say. Even here, there is a problem that this ferromagnetic coupling, ideally you would like to take it infinite, but in practice you cannot because of the precision again. So then there is a trade-off, and they quantify what is the trade-off. And in the end, they are able to, so they also defined a probability of success. And what is interesting is that, so in practice they run the annealing many times. Say that they run it 1,000 times, and then they compute the ratio between the times that you get the good solution with the times that you don't get it. By the way, this problem, I think in the end is so small that they can actually know what the solution is, probably. And then one thing that is interesting, so say that you call the P the success probability in one run. Of course, you compute it by these frequencies with 1,000 runs, but once you have it, is the success probability. And then what a lot of people think is that sometimes it might be more advantageous, instead of forcing the annealing time to become super long, you could actually keep it a bit shorter, but good enough that if you repeat now the annealing a certain number of times, you can go to decent success probabilities. So then you can compute the success probability after m rounds. So, and then this is 1 minus the probability that you fail all the times in m rounds. So 1 minus the probability, 1 minus p to the n. So this is the probability that you fail in one round. Then this is the probability that you fail in all the rounds. And then 1 minus is the success probability in n rounds. And then this they can put equal to 0.99. And they can derive what is the m, which is, it's quite easy to do. And it gives this expression derived from here. So in practice, if we put the numbers to give you an idea of how much time it takes to solve this, it's of the order of microseconds eventually. So yeah, so the total annealing time can be taken as m time, the time of a single annealing, and this is this m that we wrote here, where t annealing is 20 microseconds, and m is given by this. So, and it's something that I've seen like in many annealing papers. It's kind of general. And with this, eventually, they can get time to solution over microseconds as a function of the number of flights. And this is T99 in microseconds. And then they get something of order of 500 microseconds for, something like this eventually. And where this is 7 flights. So they do see that the time to solution to get a good success probability depends on the size of the problem, namely the number of flights. They don't have, the dependence, I even wrote it much more nicely than what they have. They have 4 points with, like, you will see in the notes. So it's not easy to see, to make a statement on the hardness of the problem, like how much it takes on a quantum computer based on this paper. But at least they went to the end. And the final success probability that they get are up to 0.7% with this, in the best scenario.
You mean that P is 0.7?
Sorry, what am I talking about? Now here they can also have to 0.99 with this.
Yeah.
I was referring to
in one round.
Yeah, in one round, and exactly, and depending on the coupling also. So this is what I was mentioning, that this JF should be infinite in principle, but eventually there is a maximum that is determined by the trade-off with the internal precision of the machine. Yeah, this is P, and then the maximum that they get here is 0.7 in a single round. Yeah. Okay, so then and then they conclude that it's too early to use the wave to solve real-world problems, basically. But I found it interesting because it had, they were trying it.
But I mean, 99% success probability in 500 microseconds, that sounds very good to me. I mean, you can even get it to 99.999.
Yeah, but eventually it became such a small problem. They don't comment so explicitly, but I believe this really doesn't take long with their laptop either. Because they had to fit it on 2000 qubits, given that you have to use this embedding.
So you get 2000 divided by 8 qubits.
No, it's what I was thinking. And then for some reason that I have to admit I didn't understand, they have a quadratic dependence on the number of the physical qubit with the number of logical qubits. I don't know why. They have like a graph. Because I would have said exactly the thing. Probably it depends also on the connectivity. That even once that you embed like this, you still have to play extra tricks that that makes it, and it's not exactly a quadratic connectivity, like a quadratic overhead. It probably depends on what is their desired connectivity with respect to the chimera graph one. So that there is still some trick to be played. Yeah, but then 84 binary variables, 2000 qubits, and this kind of size of problem, like very small. Okay. Yeah, because here you see if this was like then how many? 13 times 13 is roughly speaking, if it was a 13 factorial or 15 factorial, it's still tractable. 10 factorial is 100, so it's still very tractable. Okay, do you have questions? Okay. Then we can probably stop here, and tomorrow we're going to see the other algorithm for combinatorial optimization problems, the QAOA. Okay. Thank you.